Number 73 is asking us to find all points c on this function here so that its derivative, f prime of c, does not exist. So when we get into the idea of a derivative not existing, we could maybe try to explore this graphically, but that's informal. I'd much rather deal with it analytically. So here we go. Our derivative now, f prime of x, even though f of x is not a polynomial function because technically polynomials can't have fractional exponents, it's close enough for our purposes here, the power rule can still apply. So that derivative is going to be a 2/3 multiplied by x, and we drop our power by 1 to get a negative 1/3. Now, that's correct for the derivative, but I think it would be much easier for us to understand if we rewrote that a little bit. I'm going to keep that 2 on the top, and then, let's see, the 3 from the 2/3 is on the bottom. X to the negative 1/3 is going to become a cube root that's located down in the denominator of your fraction. So I think that would be a more practically useful way of writing the derivative, 2 over 3 times the cube root of x. And we want to know, where does this derivative now fail to exist? So what we would look for there is say, all right, our derivative is a division expression, 2 divided by something. And what's the only way that a division expression ever fails to exist? That happens anytime your denominator, which in this case is 3 times the cube root of x, is equal to 0. If the denominator equals 0 here, the derivative would fail to exist. So forget the 2. I just need to solve this equation right here. And I think you guys can see pretty quickly, I would divide out the 3, still get 0 on the right, cube both sides, and we would end up with x equals 0 as the only value right here. Now, I realize, guys, find all points c, so I probably should have replaced that x with a c right here and said, okay, c equals 0, but obviously, that's the point here. If you did try to graph this one, everybody, not one I'm expecting you to know by hand, but this is in our notes from section 3.2, kind of makes this funky little dove-shaped graph looking something like that. And what I hope you can see from that graph is that pretty much anywhere you draw a tangent line, it exists and it works fine. For example, this one right here, sure, there's a tangent. This point right over here, yep, got it, tangent. But this point right here, guys, where x is equal to 0, your left-hand tangent ray and your right-hand tangent ray are not going to agree with one another. They don't make a tangent line. I actually haven't drawn that perfectly, guys. The fact that the derivative is undefined actually tells you those tangent rays are vertical. They're both sticking straight up, and a vertical line has an undefined slope, which means it has an undefined derivative. So that's our answer here. You can kind of get to that analytically, the way we did with all of this work right here, or really graphically kind of gives you the same answer, but it's a little less formal of a way to figure it out. The analytical method is always preferable.